I am Mr. True. In this video, we're going to go back to finding indefinite integrals. Only we're going to do indefinite integration with questions that are more complicated than what we have dealt with in the previous videos or in the beginning of this chapter. What we did before we first started learning indefinite integration was we were just, we were integrating, for the most part, some pretty straightforward polynomials or equations or expressions that were very similar that had fractional exponents, which really aren't polynomials, but they're very, very similar. Here's an example. The derivative with respect to x of 4x to the fourth plus 2x squared minus 7x plus 4 is equal to 16x cubed plus 4x minus 7. Okay, so that's very, very straightforward for finding the derivative. Now, if we work that backwards then, if I say what is the indefinite integral of 16x cubed plus 4x minus 7 dx, we should get back to the original problem, except of course without extra information we're not going to really know what that constant is, so we'll just say plus c. So let's see. When we find the indefinite integral of each of these terms, just going to do it separately. So we're going to take this power, raise it by 1 and divide. So we have 16 over 4 is 4x to the fourth. We're going to take this exponent of 1 and increase it by 1, so we get 2. So 4 divided by 2 is 2x squared. And then the minus 7 becomes negative 7x plus c. So we do see that when we found the indefinite integral, we pretty much got back to the original problem, except of course, again, we don't know that constant at the end of c, or 4. Well, what happens with questions where when we did derivatives, a lot of our problems required the chain rule? Well, if a lot of questions when finding derivatives require the chain rule, then we are going to need to be able to recognize that pattern when we do integration, which we haven't dealt with yet. So our example here is we're going to do the derivative with respect to x of x squared plus 4 raised to the fourth power. Well, we have an inside function here of x squared plus 4. We don't have just a basic x like over here. So we have that inside function, which means when we go to find the derivative, we're required to use the chain rule. So the 4 comes out, the exponent gets decreased by 1, and then we have to multiply by the derivative of that inside function. So we have u as x squared plus 4, and the derivative of u, or u prime, is equal to 2x. That comes from the derivative of x squared. So if I do 4 times 2, I get 8. Now, if I take this and try and work in reverse, the indefinite integral of 8x times x squared plus 4 raised to the third power dx should come out to be this original problem. But we haven't done any problems like this. And the only way that we could find the indefinite integral of this with our current skills would be to do x squared plus 4 multiplied by itself 3 times, basically expand all of this out and get a very, very long polynomial, which then we could integrate, one term at a time. But that's a lot of work, and we don't need to do that. So I'm going to rewrite this and just fiddle with it. We are building up to basically integrating composite functions, or basically we're going to start off by working with those problems that were directly the chain rule, and then hopefully realize with some u substitution we can make these problems appear in structure to be much simpler, and work through these problems through what's called a u substitution. With this one though, because it's directly the chain rule backwards, we'll be able to do it with just recognition of pattern. But we are going to want to do this, ultimately, this u substitution, which will simplify some problems in the way that they look and simplify the integration process, and with some questions just make it possible at all. So I'm going to take this 8 and see that, okay, I have an inside function of x squared plus 4. The derivative of this inside function is 2x. I need that 2x to show up. Now again, I'm trying to think of doing this without seeing this previous problem, which we kind of do need to see the derivative process to do this, because I'm just learning how to do these problems. But thinking about just seeing this and not seeing the derivative, it's complicated, and I see this x squared in here, and the derivative of x squared is 2x. Well, out front, I have 8x. Well, if I want to split that up, or if I can split that up to be 4 times 2x times x squared plus 4 cubed dx, okay, now I can see that this inside function is x squared plus 4, and the derivative of this is 2x, so I see the derivative of that inside function now, chain rule. I want to take this 4 and move it out front, just to completely pull it away from this pattern that we have of the chain rule. So 4 times the indefinite integral of 2x times x squared plus 4 to the third power dx. Okay, now we're ready to do this indefinite integration. And why are we ready to do this? Because you see here, again, the inside function times the derivative of the inside function. But in the original problem, that derivative of the inside function isn't there. It shows up through the chain rule process. So if we're doing the chain rule process backwards, that 2x is going to disappear. But what we need is that the derivative of that inside function to be there, so we can allow it to sort of disappear through the reverse process of this chain rule, or the indefinite integral process. So we're going to have 4 times the indefinite integral of this. Okay, the 2x is here. We had to make it show up, the derivative of that inside function, but it's going to disappear as we work backwards. So it's going to be, take this, we're going to raise the power by 1 and then divide by that. So we're going to have x squared plus 4 raised to the 4th power over 4 plus c. And then the 4 out front, we're going to go ahead and distribute that. And when we do, the 4's here are just going to cancel out. So our final answer is x squared plus 4 raised to the 4th power plus c. I don't need to write the 4 times c because it's still going to just be an unknown constant, so it's not necessary. So our final answer is x squared plus 4 raised to the 4th power plus c, and that is, except for the plus c part, what we should have gotten. We saw that, again, the derivative with respect to x of this expression came out to this this expression of 8x times x squared plus 4 cubed dx. We integrated, we got back to where we started from. You will do enough of these problems to where you start to recognize this chain rule pattern, and you can do this much quicker than what I'm trying to explain or how I'm explaining it, because I'm trying to develop your understanding of it. However, you might find it a lot more simpler to work out or just look at if you do a little bit of u substitution. That's really where we're going towards. So I'm going to take this problem, this integral, this indefinite integral, and copy it over. So we have indefinite integral, or the integral of 8x times x squared plus 4 cubed dx. Okay, I'm trying to look at this. I haven't seen the original problem, and I see that there's an inside function of x squared plus 4. So we're going to let u equal x squared plus 4. Now, we need to find the derivative of u with respect to x, so du dx is equal to 2x. The whole purpose is when you do u substitution, you have to eliminate all references to the original variable of x and have the indefinite integral written only in terms of u. So I have to play around with this u expression until I can get a couple of equations over here that will allow me to go back into my original problem and do all these substitutions so all the x's go out. You really aren't going to really write this du over dx equals 2x, because you need to have that dx to show up basically on a separate side of the equation, so you can do some kind of substitution to get all the x's to go out. So I'm going to bring the dx over to the other side and have du equals 2x dx. And this is how you're going to go. You're basically going to write these two expressions here. Okay, well, I see I have an 8x dx and not a 2x dx. You can manipulate this in a couple of ways. What I'm going to do is move the 8 out front, and we have 8 times the indefinite integral of, let's move this x over with the dx so you can really see the substitution even better, and say parentheses x squared plus 4 raised to the third x dx. Well, I have an x dx in my indefinite integral, but this says 2x dx. So I'm going to divide both sides of this by 2 and get du over 2 equals x dx. Now I'm ready to do my substitution, my u substitution, and eliminate all references to x. We get 8 times the indefinite integral of u to the third power. X dx is equal to du over 2. And I have this constant of 1/2 now that I need to pull it out front as well to hang out with the 8. And 8 divided by 2, or 8 times 1/2 is 4. So we're going to pull this 1/2 out and get 4 times the indefinite integral of u cubed du. Now look how simple that is. I just have to integrate u cubed. We learned how to do that when we just initially started learning the integration process. So u cubed, the power rule for integration, just says this is going to be 4 times, raise that power by 1. I keep writing 4. U to the 4th over 4 plus c. Distribute that 4. Do you see that 4 sitting out in front of the indefinite integral symbol, the integral symbol? We had that over here when we were doing it by recognizing the pattern. So we're starting to see the similarities come up. We are going to simplify the 4, and the division of 4 cancels out. We have u to the 4th plus c. No reason to write 4c. It's still an unknown constant. And now that I've done my simplification process with the u still in there, because, hey, u is simpler than x squared plus 4, once I get done with all my algebraic simplification, and I'm basically done, then you go back to what u is equal to and plug it in. So we have x squared plus 4 raised to the 4th power plus c. Hey, that's the same answer we got over here. So at times you will be able to do integration by the recognition of the pattern, the chain rule process, these composite functions, and other times, and really you might be more comfortable just doing this u substitution to simplify the integration process. And sometimes it simplifies it, makes it visually look easier, makes it, well, better for you to do. And sometimes it just pretty much makes it possible at all. We're going to do a lot of examples because these are, somewhat complicated problems, and this is a new process for you. And I hope you learn and you enjoy, and they help. All these examples help you to do your homework. Before we get to the examples, we got to actually get the formal definition down of this substitution process. Be right back. Antidifferentiation of a composite function. Let g be a function whose range is interval I, and let f be a function that is continuous on that interval I. If g is differentiable on its domain and f is an antiderivative of f, capital F antiderivative of lowercase f on I, then the integral of f of g of x times g prime of x, see that chain rule pattern right there, dx is equal to f of g of x plus c. Letting u equal g of x gives du, which is g prime of x dx, which then we have the integral of f of u du is equal to f of u plus c. And then, of course, when you're done with that process, you'll plug the value of u back into that variable and get it back in terms of x. Should look familiar. That's what we just did in our previous problem. You're also going to see as I work through these examples many times, and you already have, the general power rule for integration. If g is differentiable on a function, if g is a differentiable function of x, then the integral of g of x to the n power times g prime of x, again that inside function, chain rule process, dx, then g of x raised to the n plus 1 divided by n plus 1 plus c, where n is not equal to -1. The integral of this is equal to that. Again, you've seen that general power rule applied as well in just the very first example we did. And this is what it looks like with the u substitution. So, let's get to those examples. Alright, well, we have the integral. We want the integral of x times x squared minus 7 raised to the 3rd power dx. So we're going to, it was always best if you look to try and find that inside function, and clearly that is going to be the x squared minus 7 that's in the other math function of this power of 3. So we're going to let's see, make sure it's a color you don't think that blends with the white here. We're going to let u equal x squared minus 7, and then du is going to be equal to 2x dx. Okie dokie. Well, if we do that, then let's see here. As I look through my problem here again, this is kind of similar to the previous one. X dx, here we have 2x dx. So we're going to want to take that 2 over to the other side. We get du over 2 equals x dx. And since this is kind of similar to the previous problem, let's just sort of pause it and reveal the answer, make sure that you get the right answer. All right, I hope that is what you got. Let's see. Hopefully I was fairly straightforward after the last example, so we're good there. I want to point out with this one, we have the integral of x times x squared minus 7 raised to the second power now dx instead of the third power. I just reduced that power by 2, or excuse me, by 1 down to an exponent of 2. So why am I showing you this? Because you don't, just because you're learning integration with substitution or by substitution doesn't mean you have to, do it with every single problem. If you can look at this and go, well, I don't really find it very difficult to, or very much time, to just do x squared minus 7 and square it. That's x to the 4th minus 14x squared plus 49 dx. Distribute this x through, and we get the integral of x to the 5th minus 14x to the 3rd plus 49x dx. And then just integrate each term separately. That's perfectly fine, and a lot of times a big time saver. This ends up being x to the 6th divided by 6 minus 14 over 4 x to the 4th plus 49 over 2 x squared plus c. Did I remember the plus c over here? Yes. And, of course, this is going to be what? 7 over 2. So you can manipulate your questions into a format which you can, integrate without the need of the substitution, or even the fact that, rewrite it so it's not a composite function, so you don't have to do it with recognizing the pattern or, again, the u substitution. Let's get to another example. Here's our next example. We want to find the indefinite integral of x times the cube root of 4x minus 5 dx. If I don't like to work with radicals, so I'm going to rewrite this with a fractional exponent, and we have the integral of x times 4x minus 5 raised to the 1/3 power dx. Now, this kind of looks like the previous examples, except my exponent is a fraction instead of a whole number. But we're going to need to really look at this u substitution a little bit slower, a little bit more, more carefully, because there's a bit more going on, and we're not going to be as straightforward as the last example. Okay, so the inside function is 4x minus 5. All right, so everything seems like the previous question. We're going to let u, always best to let that equal the inside function, so let u equal 4x minus 5, and then du is going to be the derivative of this, and then the dx at the end. Well, the derivative of 4x minus 5 is just 4. So we have 4 dx. So if we take inventory of what we have and what we need to replace, again, the u substitution, we want to take all references of x out of the problem. So we have 4 dx. I don't have a 4 over here, but we can deal with that. We can just divide this by 4. So we divide this by 4. And we have du over 4 equals dx. So I can take the dx out and plug in du over 4. I can take the 4x minus 5 out and replace that with u, but any ideas about this x? I don't have any substitutions yet that are going to allow me to get rid of that reference of x. Well, basically what we're going to have to do is we're going to have to use this first equation here in 2 substitutions. We're going to take this and, let's pick a different color here, do it in orange, and pull this out to the side, and u is equal to 4x minus 5. Well, let's take the 5 and add it to both sides. We have u plus 5 is equal to 4x divide both sides by 4, and we have u plus 5 over 4 equals x. Okay, so now I've got 3 equations that we can use. 1, 2, and 3 that we can, go back and substitute with this original problem over here and remove all those references to x, and then we'll be ready to go. So we have the integral of x, well, the u plus 5 over 4 is going to go in there, times 4x minus 5, 4x minus 5 is u, to the 1/3 power, and then dx is going to be equal to du over 4. All right, at this point, all we have left to do is some simplification, get to that nice sort of neat area where before we can just kind of use the power rule of integration to get the integral taken care of, and then simplify some more and simplify some more, and when we get done, then we can take what u is equal to, which is 4x minus 5, and then plug it back in. Let me step out and reveal the answer. If you feel like at this point you can simplify this, it would be good practice to try and do that. But I'll reveal the answer in one step and then come back and talk through it. So you might want to pause the video and give it a shot on your own to finish this, or otherwise just wait a few seconds and I'll be right back. All right, so let's see here. Where did we leave off? Oh, okay, so we have a constant of 1/4, and 1/4 that comes out is 1 over 16. And when we do that, we get u plus 5 times u to the 1/3. And of course, we're going to take that and distribute it through the parentheses. Remember, when you multiply like bases, you add those exponents, and 1 plus 1/3 is 4/3. Then we are integrating basically a cousin or something very, very similar to the polynomial function. We're going to take those exponents, we're going to raise them by a value of 1, and then divide by that increased exponent, that general power rule we just talked about for integration. We're going to flip those bases up, because dividing by a fraction is the same as multiplying by the reciprocal of that fraction. And then finally, when we get this almost done, we're going to multiply everything through by 1/16. Again, no need to write 1/16 times c, it's still an unknown constant. When we get done with all of our simplification, our algebraic simplification, and we basically are finished, then you can go back in, find u, plug it in, and write your final answer. And then when you're done, especially if it's a hard problem, bam! Woo! I'm excited. Let's get to the next example. Well, here we are. We're going to integrate. We would like to find the indefinite integral of 4 plus 1 over t to the 5th power times 3 over t squared dt. Let's see if you can identify that inside function. So set up your u substitution, let u equal what's that inside function, and then figure out what du is. And if you need to, manipulate it a little bit so it will fit perfectly with the substitution process that we're going to start to do this integration. Give it a shot now. I'm watching. Okay, so we have our u is equal to 4 plus 1 over t, and I needed to take my du equals negative 1 over t squared dt and multiply both sides of that equation by 3 because, well actually I wanted to multiply that. Look, I turned off the video to take my time, and I still made a sign error. I need that 3 over t squared to show up, so I want to multiply both sides of this by negative 3, not positive 3. Because see, I've got 3 over t squared dt, and that's exactly what I need to see for my substitution. So when I take these and plug it, these being this equation here, when I use this and this to substitute back into my original problem, we get the integral of 4 plus 1 over t is u, so we have u to the 5th, and 3 over t squared dt is equal to negative 3 du. Okay, so we're going to take that negative 3 and move it out front, and we have negative 3 integral of u to the 5th du. Okay, let's integrate that. We get negative 3 times the integral of, take that power, increase it by 1 and divide, so it'll be u to the 6 divided by 6, whoops, be writing that, times, and then square bracket, and then the plus c, okay, because I am doing the integration process, I don't need that symbol, hello. Then we're going to take that negative 3 and distribute, and we get negative 1/2 u to the 6 plus c. Now that we're done simplifying with that u in there, let's go back in and plug in what it was equal to, which is 4 plus 1 over t. So we have negative 1 over 2. So we'll just write negative parentheses. U is 4 plus 1 over t to the 6 plus c. I don't really like the way I'm writing that. Let's take the negative 1 and move it out front and just write it like this. Negative 1/2 u is 4 plus 1 over t to the 6th power plus c. Okay, now that was, maybe a little bit complicated. It's always a good idea to check your work, so let's just step off, put that check up, and get to the next example. Bam! Alright, last example. We're going to throw a little trig in here. The indefinite integral of the sine of 4x cosine 4x dx. With this one, it's going to be a little bit hard to figure out, and it really kind of doesn't matter what you determine to be the inside and outside function, because there kind of really isn't. So let's just, for the first one, say, make sure to follow my notes here, say that we're going to let u equal, let's pick sine of 4x. I like how I said that like it just didn't matter when I checked my notes. Let u equal the sine of 4x. So that means that du is going to be equal to, well, the derivative of sine is cosine, so we have cosine of 4x, but it's not just the sine of x, it's 4x. So there is an inside function here of 4x inside the math function of sine, so we have to follow the chain rule and say that this is cosine of 4x times 4 times the derivative of that inside function, and then let's not forget, of course, the dx. So as I look at what I have here, I've got dx and cosine of 4x, and here I have dx cosine of 4x, but there's no extra 4 over here, so we need to move this 4 over to the other side, and we get du over 4 equals cosine of 4x dx. Okay, well now we're ready to get all of our substitution done. So we have the integral of the sine of 4x is going to be temporarily set equal to u, and cosine 4x dx is du over 4. So times du over 4, we're going to take that constant and move it out front, so we have 1/4 times the integral of u du. Wow, look how simple this is now. So we're going to have 1/4 times, take that power, raise it by 1, so we're going to have u squared divided by 2 plus c. Distribute the 1/4, and we have 1/8 u squared plus c. Get all the simplification process done. Take u, plug it back in, and we have 1/8 u, which is sine of 4x, and it's squared, so sine squared of 4x plus c, and that is done. If you had let if you let u equal cosine of 4x instead of equaling sine of 4x, well, then your problem would look like this. What we see here is a reminder of when you work with trig functions, it's very, very easy to get an answer that is correct, but yet maybe not be the same format that's what's in the back of your book. So you want to, of course, I guess be able to get the answers in the back of the book, but you also sometimes need to be confident of the work that you did and just know that the answer that you got is correct because that trig expression that you came up with is simply in a different format than what the textbook or your teacher is giving as a solution. That's why, at least with this process of integration, we can find the derivative of our answer and make sure that it gives us the original problem and sort of check our own work. Well, that's my last example, and you know what that means? It means it's time for you to go do your homework.